Okay, so we're going to get started with the biostats portion. Um, so Dr. Smith taught us biostats and Dr. Ramdas taught us the epidemiology. So we had different slides than you guys, but I knew y'all wanted to obviously see your slides instead of our old slides. So I just went ahead and went through your material instead of my old notes. So we'll go with that. I just want to say that I found some of the biostats material difficult, but I did okay on the exam. So if you find some of it complicated, just know that a lot of the exam questions are not as bad as some of the practice stuff and all that.
Yeah,
All right.
it was difficult, but it wasn't as difficult as I anticipated on the actual exam.
All right, so we could get started with some basic definitions. When you talk about quantitative versus qualitative, right? So we're talking about numerical versus categorical. Nominal basically means naming things such as colors. Ordinal can be subjective, such as pain, right? Pain scale 1 to 5 or whatever. So you want to just know these just in case they ask you. Those would be easy points. And you could further break these down into these different categories, interval and ratio, depending on the circumstance. So just know these definitions and you'll be good there. Also, just being able to break it down in case they give you an example such as height or temperature, just knowing which one falls in each. And obviously, as you go from left to right, they become more detailed, right? Nominal being just a color, and you can kind of get more information through a ratio, right? A true zero value. Now, everybody knows mean, median, and mode. I don't want y'all to get confused because these can be easy points on the test. So mean, of course, you're just calculating the averages, add up all the numbers and divide it by the values they give you. Median is going to be your middle number. So the trickiest way they could do this for you guys is, well, what's the median number here or the middle number here? Just remember, if you get two numbers, you have an even number of variables. If you get two numbers, you just take the average of those two. They did put one of these just like this on our exam. But what if it's like 10 and 11, right? So you would take the average 10.5. It doesn't have to be a whole number. Okay, so just make sure you know that. Now, if you're talking about mode, we're talking about the most common number, right? So you can actually have multiple modes. There's no averages going on. So if you're calculating mean or median, you're going to have one number as your answer, but you could have a multimodal answer, right? So here you could see 4 and 15 are both considered modes. So this would be sort of like a bimodal distribution. And this is actually common. You'll see these in certain cancers or a lot of diseases, right? So you see this bimodal distribution. Some breast cancers you'll see happen mid-20s and then at menopause, right? So you can see this bimodal distribution. So just keep that in mind. They could give you something like that, right? And you can see that here. So the modal distribution is this. But we'll look at some of the skewing just in case they ask you guys about that too. Pretty straightforward. You've seen all of these different types of graphs before at this point. If anything, you have obviously seen histograms, but maybe you didn't know it was called a histogram. So it just kind of breaks down. It's kind of like your grades. Your grades are distributed as a histogram, like how many people got each score, right? So we classically see this bell curve when we look at grading scales, but just as an example, keep the histogram in mind when you're thinking about like your grades, right? Right, and this is our normal distribution, our Gaussian or bell curve that we're used to looking at. So we'll look at that a little bit more detail later. So, and then there's some calculations when we look at the whiskers and the box plots, where you're trying to account for outliers, right? So sometimes when you have these outliers, it skews the data completely out of the way. So at some point you have to say, at what level do we say these are not significant towards our data? And that's what you use those whiskers and the box plots, which we'll get to in a second. Because theoretically, you can have 100 people that you're taking a test for, and one of those people may have a 1 in a million disease, right? It's not likely, but it's theoretical. It could happen, and they would be an extreme outlier and skew the data. So we'll look at that in a second as well. Now, we'll look at these. Range is just kind of like what from top to bottom are your complete scores. You can use grading systems here too. Just remember, when you do these, you're not taking averages, you're taking the median, right? So the first thing, you take all the data and you find the original median. That's going to be your Q2. That's a Q. Q2. And then from that, so you have half the, actually, let's try to do this. I want to see if this works. This may be easier. Me and Kishore tested it out a little while ago. All right, yeah. Okay, right. So take all your numbers and you get your Q2. That's going to be your variable in the middle. So half of the numbers fall below it and half of the numbers are going to be above it. Uh-oh, it's a little delayed. Sorry, guys. So from that point to find Q1, you're taking the median again, right? Median of the lower numbers and the median of the upper numbers. So that's all you really need to know for these. And then you have your 3 ranges. And then the inter range is going to be interquaternary, something like that, is going to be your Q1 to Q3. Okay. And then we'll look at in a second where you actually use the whiskers to determine at what point are the outliers too far out. So key point here is that you want to, use this over there. That we're worried about medians here, okay? And that's how you calculate that. Now, if you want to see it in words, this is kind of what we looked at here. And again, if it is an even number that you're looking at, you have to average the 2 middle numbers. So this is what we're talking about. What are the whiskers? These are the whiskers, these purplish lines that come across. So anything outside that data set is considered outliers. We're not necessarily going to, put this in our research paper. They may skew the data too much. So when we're determining the whiskers, it's Q1 minus 1.5 times this range here, okay? I don't know if they make you calculate that, but they may give you this graph and ask you where the outliers are or what points. They could really go any way with it. All right, so you're familiar with this. This is our normal range, and it's kind of just taking this box plot and lying it on a graph. But look, this isn't necessarily standard deviations here, right? It doesn't correlate exactly to it. But we'll get to that in just a second. Variance is kind of weird, right? So you take the distance from the mean and square it. That's fine. But to do the standard deviation, you take the square root of it. So you basically just go backwards, right? So the variance is squaring it. You square the number, and then taking the standard deviation, you take the square root. So you're basically back to X. So whoever made standard deviation didn't like the guy that made variance, I guess, and he decided, let's just go back to that. But when you do the standard deviation compared to the variance, you're squishing your plots down, right? So you're getting smaller numbers, so it's more of a linear distribution. It's just the easier way of doing it. I remember Dr. Smith explaining that to us. I don't know, it kind of made sense if the numbers are closer together. Right, and so you would expect in a normal distribution, this bell curve, right? If it's a proper bell curve, everything will equal each other. The mean should equal the median, should equal the mode. So that's how you distribute it. Fair question, they could ask you that. And then we'll look at the skews in a second. Now, these numbers are going to be very important. When we talk about 1 standard deviation, 68% of the grades or whatnot should fall in between that. And then if you go to 2 standard deviations, 95 should, and then 3 standard deviations, 99.7. So you definitely need to remember these numbers down here to know what falls within what. I think the trickiest thing they could do is if they say some person fell below the average, below the mean, but they were still within 1 standard deviation, okay? So how would that work out? If they fell below the mean, right here, but they were still standard deviation, you don't want to put 68% because they're below the mean. You would get this 34%, okay? Hope that makes sense, because so it's important to know not only the standard deviation, but sometimes if they tell you which way you fall, to know you have to half it from the original number. Okay, I think that's as difficult as they can make it on you guys. You probably came across some practice questions like that. So they like these numbers a lot. So make sure you know those. A little bit more of the same. So it's 1 standard versus 2 versus 3. You can see that there. And this is just from first aid, kind of outlines everything for you guys. And we'll look at standard error of the mean in just a second. All right, so what are we looking at here? So, you know, we can still appreciate the fact that here our mean and median and mode are all going to be the same, right? But what's different? Well, our standard deviation is different. If we look at the yellow line, our standard deviation is right there versus the blue line is kind of centralized, right? So what would you consider a more, okay, so say you were writing a test, what would you want better, right? You'd want, you know, you'd want it to be a closer or a lower standard deviation, right? Which means the students kind of fell in a better range, a more, you know, the values didn't fall, you know, erratically around the mean. And, you know, that's with any research paper or whatnot. You kind of want your numbers clustered toward the center, because that kind of gives you more validity to it. And what you'll find is, and this is kind of a good point to be made, that's kind of where standard error of the mean comes in. The increased number of data points you have, subjects, test scores, whatever, the closer you're going to get to the mean. All right, the closer you're going to get to this blue line. And that's just because statistically, the more values you have, the more you're going to fall around the average. Now, you may have a few outliers, but when you look at the entire dynamic situation, you're going to fall more towards the middle. So it makes the more values you have, the more valid test, right? That makes sense. The more subjects you have in a research or in some sort of trial, the more valid it will be. Okay, so yeah, and this is kind of what I was just explaining here. So smaller becomes narrower, and then if it's larger standard deviation, it becomes wider. So they very well could ask you that on the test, giving you the different graphs. Now, this is fairly straightforward when we look at precision versus accuracy. So precision, yeah, I have a better illustration of this, yeah, coming up. So precision is like clustering, okay? Like if you were shooting at a target, these clustering. Pull up the pen, come on. Or not. You can see here that there's clustering, right? They're precise. When you shoot the gun, they all come out in a cluster, right? So this shows high precision. Means everything, all the shots fall in a certain range. Now, accuracy, you're trying to, this is where you're shooting for. All right, so you have precision, you can pinpoint it, but you're not shooting at the target. So if you look at this graph here, you can see that it is accurate. You know, if you average all these out, they kind of fall towards the middle, but they're not exactly precise because they're not in a clustered set. Ideally, you want everything accurate towards the bullseye and clustered, which will give you increased precision. I do have another picture coming up later on when we talk about it. But yeah, so I remember we did have a question like this. They gave us these little bullseyes, asked which one is precise and accurate or whatever. So easy points there. All right, so when we look at skew distribution, you always define it by which way the tail is going. So negative skew, right, if you want to graph, is going to be pointing to the left. A positive skew is going to be to the right, right? And then we'll look at coming up. Okay, this is super important. Whenever you have skew, so which way is this skewed? Positive skew, right? The tail goes to the right, positive direction. This is always going to be the case. The mode is going to be in the middle, right? The most common number. The median, the middle number, will be next, and the mean will be the furthest. So you would always expect the mode to come first at the peak, the median to come second, and the mean to come third. The mean is going to be always towards the tail, whichever the tail side is, right? So if we looked at this the other way, right? If we had a tail this way, like, whoops, that's awful. Okay, like that. Actually, let me do this. if we had a tail like this, it's not even very good. Let's see. We'll call that a tail. All right, so always find the mode first. That's your top point. Median comes in, so we have a negative skew, right? Negative. Median's going to come next. And then the mean will be third. All right, very straightforward. I just wanted to point this out for you because I would venture to guess that you will have a question like that. All right, cool. And you can see this here. Again, we talked about this bimodal distribution, and then whichever way you're looking at it, find the mode first. That's your top peak, and everything else falls towards the tail, median next, and then mean. All right. Okay, super easy way. When I was looking at this in first aid, a light bulb went out. Super easy way to define what test you're looking at. We don't talk about this one to my knowledge, this Fisher's test, but let's talk about t-test, ANOVA, and chi-squared. T-test and ANOVA test are always going to be looking for averages, okay? So if you're looking for an average and you have two variables, it's a t-test, T for 2. And if it's 3 or more variables, you're going to use ANOVA. So all you need to do is look, and if they're asking for a mean or the average, it's one of these two. Now, if you're talking about categories, but they're not necessarily looking for averages, no averages involved, they just want categorical, then you use the chi-squared test. So that's the easy way to do it. Ask yourself, are they looking for mean? Yes. How many variables? 2 or more. 2, t-test, more than that, ANOVA. If it's categorical, then you just use the chi-squared. Okay, not averages there. Piece of cake. All right, same thing here. T-test, ANOVA, gonna do means, chi-squared, categories, no averages involved. All right, and then regression analysis is kind of a way to make some sort of linear distribution. If you could bring everything down, your variables into a certain plot, then you could kind of define it for research and whatnot. Okay, and you could see some of these plots are different patterns here, but they all are considered regression, right? Because you can appreciate some sort of distribution, some sort of predictable distribution between them. Okay, and then a linear correlation. What we'll talk about is the Spearman's and Pearson's. Yeah, the Pearson's correlation. So if there's linear, remember when we talk about some sort of linear distribution, it's y equals mx plus b. Y'all remember that, where m is the slope of the line. So these linear correlations, if we were to make here, you would say, I would consider this a Pearson's, right? Because you can get a linear distribution here. So, and we'll get to that, and here it is, right? So the key thing, it should be fairly straightforward on the exam. If you're looking for some sort of linear relationship between variables, then you use Pearson's. The way I think about it is Spearman's is kind of like, it's more, you're taking more, well, it's non-linear, right? So you're taking more, I don't want to say erratic, but like wider variables, right? You're taking two different sets and overlaying them to see if you could see some sort of similarities between them. Okay, so the key thing is that with Pearson's, it's going to be a linear relationship. Increased BMI with increased chance of heart failure, right? People that tend to be obese tend to have increased atherosclerosis and whatnot. So you see with increased BMI, increased risk of heart failure or stroke or whatnot, or diabetes, something like that. Linear relationship. So they use R as the variable. So anything, when R is close to 1, you consider it a strong relationship. When it goes to 0, there's no relationship, and less than 1, it's an inverse relationship. Okay, so like we were saying with BMI and diabetes or whatnot, you would expect it close to 1. Okay, 0 is no relationship, and if it's negative, as in one value, as it gets lower, the other value goes higher, there's an inverse relationship, right? They're inversely proportional. And so, yeah, so look, this is perfect because look, these are completely inversely proportional. We're looking at a -1 here, right? versus, they don't give us a positive one. A positive one would obviously be, it would make an X. It would go the exact opposite way. But the closer it is to 1 or -1, the straighter the line is going to be. You can see here, you can't really draw a straight line through this because there's no relationship. Okay, so fair game, they could ask you that, which one, they'll give you some values and say which one's the best for Pearson's correlation, or which one's the most proportional, positively or negatively. So that's our R value. And again, this is from first aid, so it's definitely fair game if it's in first aid. That's always the first place I look to see if this stuff's important or not. So you could see these correlations here. All right, now Spearman's, we're not looking at a monotone or a linear distribution. We're looking at nonlinear things. So you could take two variables that if you plot them, they don't necessarily fall in the same line or category, but you're just looking for some sort of relationship between them, okay? So by doing that, the key thing is, I believe in the STEM, they would put some sort of nonlinear relationship, okay? So it still can be considered a monotone relationship, as in, so like Pearson's would be a linear relationship, right? So that would be a Pearson's, right? And then if you had Spearman's, it may be, the relationship may look like this, right? There's still a relationship. You can draw a concurrent line through it, but it's not necessary, it's not linear, obviously. So, you'd have to see, so just look at the values. Hopefully they'll give you a nice little graph or something and you could do it. But if you're in doubt, look for the linear versus nonlinear relationship to determine those. Okay, and then they use this row.
I wanted to chime in first.
Yeah. I'm not hearing you.
Hello?
Yeah. I don't know if it's,
Your audio is really choppy.
maybe send it in the chat and then I'll look at it in the break. Okay, now standard error of the mean, as was mentioned briefly earlier, is like standard deviation, but you're taking into account the number of variables, the number of subjects that you're using. So it's more of it's a better example or a better testing solution because you're taking in more factors to it, the variables or the number of subjects. So you can see that here, right? And the key thing to remember here, like I mentioned earlier, is the more samples you have, the lower the standard error of the mean is. Okay, so by increasing the denominator, if you have increased number, then your standard error of the mean right? So this is a better test, right? You have less variation here. This is a better test. The more numbers, so if you do some sort of clinical trial, the more number of people you have, the more variables, the closer you're gonna cluster around the mean. So it's considered a better test, which makes sense in practical terms, right? You don't want to do some sort of clinical trial with like 5 people. You'd rather have 5,000 people, right? You get a better analysis. Okay. And again, this is kind of, this is kind of explaining what I was just talking about.
Hey, Brady, I have a quick question.
Yeah, sure.
You know when we use n versus n-1?
I'm sorry, what? Where?
When do we use n versus n-1?
For calculating SEM?
Yeah.
Yeah, this is the only equation that I think you need to know. I'm not familiar with using n-1. Yeah. I think, I mean, somebody can chime in, but I think this is the whole point of the, yeah, go ahead.
Typically for whenever you're using the difference between n versus n-1, is the big N is for populations, n-1 is going to be just for a sample.
Okay, thank you. For the test, you won't, I don't think for these equations, we'll get to the equations you need to know, but for these equations, it'll be all theoretical. So the point I wanted to make here is that the number in your sample is going to be super important, because the higher the denominator is, the lower the actual standard error of the mean is going to be. Okay, so this will be one of those questions. Remember, I had mentioned when we talked about the advice session that a lot of these questions, sort of like the IMCQs, are all theoretical. Once we get to the epidemiology, those are the equations you really need to know. But for the stats, this is the thing to focus on. But thank you. All right. Right, so when we talk about confidence, right, this is our confidence interval. We accept science, or whoever decided, they had a big meeting and they decided that 95% is going to be our confidence interval. So we accept an alpha, which is our error rate of 5%. Okay, so if we have a 95% confidence interval on any research paper or any study we do, or anything 95% or better, we consider it valid, right? So that's when we talk about our null hypothesis and whatnot. So significance level is going to be our alpha, right? So we're looking for an alpha error. As long as our p-value, okay, I don't want to get ahead of myself. So this is what we accept. So this is the same thing as saying we accept the 5% error, which is the same thing as saying we have a confidence interval of 95%. Right? We're 95% confident that the values we take will fall into this range. All right. So if we accept an error rate of 5%, anything less than that, we accept the hypothesis, which means we reject the null. It's very counterintuitive, or it seems very silly, but it's like saying I agree with you is the same thing as saying I do not disagree with you. Right, so if we accept the alternative hypothesis, or the hypothesis that we're looking at, we're also rejecting the null. So we're saying, I agree with you, or I do not disagree with you, but they like that do not disagree thing. Mathematicians, right? Okay, so yeah, and this is our 95% confidence. We'll talk about the two-tailed test in a second, but you can see that if we look at the 95%, that would fall in here. And then our alpha error would be distributed evenly between both tails. But I have that coming up in a second. So if we say our confidence level is going to be, so we accept it as 95%, right? So 95 would equal, oh, it's down here, sorry. Yeah, this right here, right? So 95%, that's where we stand. And let's see, right, and as it correlates, 95 is right around the 2 standard deviations. Okay, so remember 68% will be 1, 95 will be 2, so anything that falls within the 2 standard deviations will be considered valid. It's a little bit different. They just accept 95. I think there's a point value, 95.7 or something, but it's close enough. So your Z-score, which is some voodoo the school does to figure out our grades, all that Z-score is it figures out exactly how far you are away from the mean. Now, if you're asking about how the school does it, I think they use some sort of modified Z-score to scale everybody up. They don't actually, until term 5, I heard, they in term 5, they do scale some of the scores down to make a true bell curve. But technically, as I've seen so far, it's always a modified, so it scales up. But yeah, so it just, all your Z-score is going to give you an exact value of how far you are away from the mean. Not just 1 standard deviation, but it'll tell you like you're 1.56. And then you can multiply that by the difference from where you are to the mean, and they can figure out what kind of curve to give. I don't know if they'll even ask you a question about this, but it was in your notes, so I figured I would add it. All right, now, again, I'm hammering home this point because it's very important. The increase in number that you have is going to decrease the error, the standard error of the mean, right? Because our n is in the denominator, right? So if that's the case with the n in the denominator, the increase in number will give you a decreased standard error of the mean. okay, standard deviation, right? Okay, that's the whole point. Okay, just in case some of these values, I don't think they'll ask you to calculate, but if it's some sort of ancillary data in the actual stem, 1.96 of your Z correlates to 95%, but technically you're supposed to have a table to figure these out, but these are common numbers, especially the 1.96. So if you do see that, just know that correlates to 2 standard deviations. All right. Right, again, okay, so now we're going to talk about the errors, right? Yeah, so a type 1 error is the same thing as having an alpha error. And actually I have more for that coming up in a second. So let's look at this. So if we say this is our alpha error, this dotted line right here, that's our alpha. We accept anything greater than 95. If this p-value, we need p to be less than 0.05, right? And if P is this blue shaded region, you could see it falls less than this, right? So maybe like 0.04 or whatnot. So we can say that this is statistically significant. We accept the alternative hypothesis or the hypothesis we're talking about, but we can also reject the null hypothesis. We agree with it. We also do not disagree with it. Yeah, so, and you can see this, these are just some definitions from first aid. Okay, so the p-value is going to be your generated for your statistical test to tell you basically what your confidence is in it, right? So the p-value is not, and this is very confusing, it's not saying that the null hypothesis is necessarily true. It's saying that you can't reject it. Okay, you can't say it's not true. Okay, so you're not saying the test is necessarily invalid. You're saying that there's no valid way of saying that the test is better than chance. Okay, I hope that made sense. Because if you're saying within 95% confidence that your hypothesis is different than chance, right? That by doing this specific thing, it's gonna lead to a certain result. If you don't have a 95% confidence or a p-value that's less than 0.05, you're saying that this hypothesis is not necessarily true. It may be true in some circumstances, but not all the time. Okay, not confidently. Okay, so those values that fall into that range of 5% are considered chance, right? So if you were, it's hard to think of an example. If you were to say a certain situation happens under these circumstances, right? You want to say in 95% confidence, this situation happens under these circumstances. But you can't, your p-value is greater than 0.05, then you can't say necessarily that that's the case. You're saying that it also happens by chance. It's not necessarily the circumstances you were looking at. Okay, I hope that made sense. Unfortunately, some of the simplest explanations are still very complicated because you're trying to put these number calculations into words, and unfortunately, that's how your test is going to be, though. So I hope that made sense. So you're looking at differences here. So the probability and the p-value is equal. P-value or more extreme, or your circumstances are different. So whatever your alternative hypothesis is, you're saying that there is a difference from just chance. Okay, this circumstance you're looking at will happen under these conditions, and this is against this circumstance, obtaining the study results by chance if the null hypothesis is true. Okay, so if you, what's up?
Can I point something out?
Yeah, sure.
The p-value in the first problem set that they gave us, number 5, that question shows a really great example of how Dr. Ramdas might test us on it, because I asked him questions before. And so just when they're asking what is the meaning of the p-value in the study is different from based on this p-value, what can you interpret from this study? And so if you look at number 5 from the problem set, the answer is number D if they want to know the p-value, what the meaning of the p-value is. But if you're using the p-value to interpret the study, then that's when you would use C. So I just clarifying how they might test us for p-value.
Okay,
Can
awesome.
you go ahead and read those answers real quick, just so that we're all on the same page?
Yeah, I
Okay.
don't have the problem set.
So do you guys want me to read you the problem?
Yeah, sure.
Okay, so a 45-year-old man comes to the physician because of a 1-month history of side effects associated with atorvastatin. He wants to be prescribed pantoprazole. He shows the physician results from a study that demonstrate a lower mean number of heart attacks among patients taking I can't say the word, when compared to those taking atorvastatin, with the p-value of 0.01. Which of the following best describes the meaning of the p-value 0.01 in this study? The answer is, if there is no difference, the chance of getting a result this extreme is 1%. That's what the p-value means. But if you wanted to, if the question asks, how does the p-value interpret the study? The answer would be, this is a real medical advantage of switching drugs. There is a real medical advantage of switching drugs.
Okay, yeah, so by saying taking these two drug combinations, you could say that it is within 1%, 0.01%, in that amount of, so 99% chance that those two medications together will correlate in a benefit. 1% of the time, it will not, okay? But that means that's a valid reason why we would use this combination of drugs. Okay, so anything less than 0.05, maybe you would say that it's not beneficial. But then, and then we'll look at it in a little while when you talk about looking at from a clinician standpoint versus the statistical standpoint. But statistically speaking, you would want a p-value of less than 0.05. Okay. And then the lower the p-value, more unlikely the null hypothesis is. So like in that situation, we had a 0.01. So that's only a 1% chance that it would fall outside that range, the p-value, and that's acceptable. All right. So we could reject the null hypothesis. We could say that those two medications together show statistical evidence that it would be beneficial to use them together. Thank you. All right, so again, p-value less than alpha. Alpha is our error rate. If we accept that as 0.05, if the p-value is less than that, we show statistical significance. Now, there are certain circumstances where, you know, in a clinical setting, you could say, well, look, it's you know, only 2/3 of my patients show benefit, but at least some of them do. So there is a difference between when you're looking at statistics versus the actual clinical situation. But I have a slide on that coming up. Okay, so this is super important. Just breaking it down, if you p-value is less than your acceptable error rate, there is a difference. So there is a difference in using these certain medications together. It's not just, the combination is not just happening by chance, so you can accept it. And then if it's greater than or equal to, you do not reject, you don't accept the null, but you can't necessarily reject it. So again, this is not necessarily saying that the null hypothesis is true, you just can't rule it out, okay? And okay, so this one-tail test, obviously the whole 0.05 or 5% will fall on the one tail. But if you look at the two-tail test, you have to split it. So we still, on a two-tail test, we still have a 95% confidence, but you have to split it half and half, so 0.025. Now, type 1 error, definitely need to know this correlates to a false positive. So this is our alpha, significance of our alpha. So a type 1 error is going to be the chance of getting a false positive. When we look at type 2 errors, that's going to be our false negative. It's considered a beta error. Now, it's important to correlate the power of a study. So this is like saying the power is 1 minus the false negative, right? So the lower your beta error, the stronger it is, right? Because that's the lower error rate. So 1 minus this will give you a strong power statistically. So if you look at this, you could correlate it like this. The null hypothesis would fall here, 1 minus your false positive, and then your alternative hypothesis will be 1 minus your false negative, right? Which technically would be true, right? You just you're getting a negative value, but it's incorrect because it's false. So these are all your positives. So this is your power. If you have a low false negative rate, that can correlate to you being able to reject the null or accept the alternative hypothesis. All right, and then you could see this here. Y'all are familiar with this. If we break it down, you could see these are where everything falls. And I'm sure you're aware by now that on the exam, they're going to give you these tables, which in my opinion makes it infinitely easier. I found the hardest thing, especially with the practice problems, was figuring out where everything went. They'll give you like the total, and then you have to divide it into the boxes. They're going to give it to you. And I know y'all had a small group where the box was flipped or something like that. They're all right. Okay, so the disease will be up top and the test will be on the left side. So they will be correct. They're not going to trick you. They did it right for us. So as long as you know which box correlates to which, it should be pretty easy. You could calculate, all your sensitivity, specificity, negative and positive predictive value. Okay, so this is again from first aid. If you want a little explanation for it, you can see that here. And this is what I was talking about. So there is a difference statistically versus clinical significance. Statistically, you're just worried about the values. You're not worried about the symptomology or the outcome. But so you're saying what are the values here? Can we reject the null? Is it the p-value less than 0.05? Yeah, okay, if that's the case, then we're good here. But clinically, it's kind of more of a subjective approach to it. What is happening to my patients in this situation? There are different variables that come in. We did have a question, so this is easy points if you could differentiate these, and they give you little explanations here. So definitely make sure you look at that. All right, so we'll do epidemiology. We did have a question on this. So being able to differentiate the different tests. Remember, screening kind of falls in the middle. So first, this primordial is going to be population prevention. So things like taxes, cigarettes, seatbelt laws, you can help. You kind of like this umbrella overlying, so laws and stuff like that. Then you have a prevention approach. So that's primary. So no smoking, seatbelt, stuff like that. Secondary is going to be your screening. And then tertiary is after you have the disease. So you're assuming the patient obviously has diabetes. So diabetic foot care would be some sort of tertiary approach. So you already have the disease. So remember, secondary screening, you can do S&S. Tertiary, prevent. So tertiary means you have the disease already. Prevent problems overcoming problems. Quaternary gets a little confusing, but it has to do with the treatment. I don't think y'all will get a question on that. It'll probably be one of these three: primary, secondary, or tertiary. And so there's some good examples here for y'all. Now, don't get this confused with this. Don't get that confused with this, because this also has words like primary, secondary, and tertiary, but this is levels of disease prevention. So in this situation, you're looking at whether the person has the disease or they don't, and what level they're at. So in primary prevention, the patient is at risk for having a problem. Secondary is early or you're asymptomatic, so some sort of viral infection. Maybe you contracted COVID, but you're not symptomatic for it yet. And then tertiary, you have established disease. So each of these steps are going to correlate to different treatment regimens, okay? So make sure you can correlate these, but know that even though they have a lot of the same terminology, they are different. All right, now, like I said, they'll give you the tables. So the hardest part about calculating these is going to be putting these in the right place. Then it's just plug and play, right? Then you could just, whatever they're asking for, sensitivity, specificity, whatnot, you just plug in the values for it. All right, so remember, like I said, they will do it right on the exam. I remember we were worried about that too. What if they flipped the tables, but they didn't. So disease up top, test on the side, and then you could figure it out. So I have a different slide for that. But remember, sensitivity, what you're looking at is at all people with the disease, okay? That's how I like to think of it. So you have your true positives, they have the disease, over true positives plus false negatives. Do false negatives have the disease? Yes, they do. The test just came back false. It was a false negative, but they do have the disease. So sensitivity is testing all people with the disease. Specificity is testing all people without the disease, the people that truly don't have the disease and tested negative, but also the people that came back false positives, right? They don't have the disease, the test just came back bad. Okay, incorrect. Now, when you do positive predictive value, you're looking for all the positives, true positives plus false positives. Negative predictive value, all the negatives. Okay, so don't get it flipped up in your head. That's kind of how I made sure that I didn't mix them up. Some people like the spin snout thing. I don't know. My thought process is this. Okay, so if you want to, why do you want a highly sensitive test as your screening test? Well, we could take COVID, for example. The point of a highly sensitive test for screening is that by no means do you want somebody that has COVID walking out thinking they don't have it. Okay, so a highly sensitive test is going to catch all the people that have the disease. Okay, now the sacrifice of that is some people are going to test positive falsely. So you're going to get some false positives. But the whole point is you don't want anybody walking out of the building that has COVID testing negative. Okay, so you want a highly sensitive test to screen. Now, it kind of does suck to a degree because let's say we're tested for cancer. Some people are going to test positive for cancer that don't actually have it. Okay, that's not good, but it's better than sending someone home that has cancer that thinks they don't. Okay, so your first test, your screening test wants to be highly sensitive. Make sure you catch all the people with the disease. Then, so in that vein, you're gonna some people are gonna test positive that don't have it. So then you can get to a more specific test and you could say, okay, let's just make sure anybody that tested that was a false positive, we can rule out. Okay, so however you look at it, in and out versus, you know, the snout thing just does it the inverted way. Highly sensitive, when it's negative, you rule out the disease. Okay, so it just depends how you want to do it, if this helps you out. But the way I think of it is like highly sensitive test, if you come in for the test and you have the disease, you're gonna test positive. Nobody's walking out the door with the disease testing negative, thinking they're okay. Okay, so if you just think of it like that, you're good. All right, then after that point, you go to specificity and you could see any of those false positives, you could rule those out. Okay, I hope that made sense. We're good? Good, all right. And you could see that here. So when we talk about positive predictive value, so the probability that a true positive is actually a true positive. Okay, so this is now, instead of looking at the disease pattern like sensitivity and specificity, we're looking at how good the test is. Now, unfortunately, when you look at these equations, they're kind of just moving around variables, from numerator to denominator and whatnot. But you have to be able to translate this into words. So keep in mind, I'm just going to go back, that sensitivity and specificity, we're looking at the disease pattern. Okay. And when we look at positive and negative predictive value, we're looking at how good the actual test is. Okay, so let me go back to this real quick. Specificity, remember when we put disease up top and test on the side, sensitivity goes down this column. We're looking at, remember, disease up top. Actually, it says it right here. Disease up top, so sensitivity, we're worried about the disease. Everyone with the disease. Specificity, everyone without the disease. Positive predictive value, how good the test is positively at predicting positive results. Negative predictive value, we're going across horizontal, we're looking at how good a negative test is, okay? So you just kind of have to work with these. So again, if your negative predictive value says, I walked into it and I got a test, I tested negative, how do I really know I'm negative? With what percentage do I know I'm negative? Right, so what's the possibilities? I got a false negative, right? So you could say it's a 99%, or like the antigen test used to be 88%, right? Now they do PCRs for COVID, but the antigen test was 88%. So you could say the negative predictive value, I got an antigen test, it came back negative. So I could say with 88% confidence, I'm actually negative, which isn't great. Now they do the PCR thing, but that's the idea. So again, sensitivity, specificity, you're looking at the disease pattern in the vertical columns. Positive and negative predictive value, you're looking at horizontal, you're looking at how good the test is, positive versus negative. All right, hope that made sense. Same thing here. just a little bit different. I think that was from the notes. All right, and same thing here, right? I'm harping on this because this is very important clinically. And so they're going to test on it, but they'll give you the tables. This should be easy points. All right, disease patterns, positive, negative. Any questions? I don't have the chat up because I don't have my other screen. Going once, going twice. Are we good? I'll take that as a yes.
I
All
have a
right.
question.
Yeah, sure.
How does the NPV relate to the sensitivity? Because in that one clip down there, it's if NPV, I'm trying to wrap my head around that. Like if
Yeah.
NPV goes up, it increases with highly sensitive tests?
So
or-
yeah, so this is a little confusing, but I'll show you how. Sensitivity correlates to negative predictive value. Why is that? Okay, so negative predictive value is true negative over true negative plus false negative. Now, right, where is that right? True negative, okay. And then
Does that have to tie into that snout thing where it's
yeah,
like if
so
it's
you could,
negative,
yeah,
it
that's
rolls
how
it
they
out?
do that.
Okay,
And then
that's
it's
the-
spin, snout, spin, spin, specific. No, I'm sorry, that's the other one. It's see, I don't use that, but people really like that. How do I go back?
It's snout. If its sensitivity is negative, it rules it out. So
Snout, yeah, out. If it's negative, then it rules it out. Yeah. So the false negative false here. See, I was looking at this. Okay, so here, I'm sorry. Okay, yeah. Okay, so the whole point of a highly sensitive test is that you don't want anybody to walk out with that, right? Let's say we have COVID.
right.
The whole point is nobody's allowed to walk out of your office with a false negative result. This is how I wrap my head around it in like words versus numbers. So this is a no-no. Nobody with COVID is allowed to have a false negative test, all right? Nobody's walking out of the office thinking they're negative, but they actually have the disease. This person who is false negative right here, they are positive. They're positive for COVID. They have the disease, all right? So the whole point is the higher the sensitivity, by increasing your sensitivity, you're decreasing your false negative rate. You're decreasing the chance that somebody's going to walk out of your office with a negative result when they have COVID, correct? So highly sensitive test correlates to a high negative predictive value simply because we're looking at decreasing our false negative rate. Does that make sense? Yes, no?
Yes, thank you. Yeah, I
Okay,
see it
yeah.
there in the like the math. Yeah, I got it. So
Yeah, just go ahead.
an increased PPV would be a increase in specificity.
Right, exactly. It's the exact opposite. So specificity would specific tests or high specificity would correlate to an increased positive predictive value. So in the other, yeah, and so you could use that spin snout thing for this, but I like it just because in case they put it in, in words on the test. The whole point of a highly sensitive test is we want to eliminate our false negatives. All right, nobody's allowed to walk out with the disease. And you can see in the negative predictive value, this in the denominator. We want to keep that as a low number. Okay, that's how I wrap my head around it. But if you want to spin snout, that's fine too. Just get it right on the test. All right, cool. Now, just more equations. On my drive in the additional resources, it's like a one-page document. It's got all the equations y'all need. It's typed up, somebody did it. So it's all there. I put little snippets of it in here for you guys too. All right, so now let's talk about prevalence and accuracy. Same thing, they're gonna give you the table. You have to figure this out. So what's the difference here? Prevalence is, we're saying, everybody with the disease over the total amount. So how prevalent is the disease in population? 5% of the people have it or whatever. So the numerator has to have all our true positives plus all our false negatives. Do the false negatives have the disease? Yes, they do, right? So they count towards the prevalence of the disease. So we take our true positive plus false negative over the total population. Okay, so this prevalent, put it in the category with sensitivity and specificity. We're worried about the disease here. Now, accuracy, this is sort of like positive and negative predictive value. We're worried about how good is the test. So here we're saying, how accurate is the test? True positives, true negatives over everybody. What percentage do we get right? Okay. All right, cool. Now, let's see. So one of the situations you can have, so this is important. So make sure y'all look at this little table because they get asked y'all about these individual situations. But the prevalence, the more chronic a disease is, the more prevalent it'll be, right? Because people will live long with the disease, so it'll be greater than the incidence. If they equal each other, they're going to be dying off because the incidence is going to equal the prevalence. But with more chronic diseases, you're going to just be adding the incidence. You're going to be, each time you get a new person that has a disease, you're going to be adding it to the prevalence. So the disease is prevalent in population. So you're not necessarily getting a lot more people, like the incidence rate isn't going up very fast, but because these people are living longer, the prevalence is going up, okay? The prevalence of the disease. Now, the thing I wanted to point out here is when you have some sort of novel treatment that you're doing, some sort of new chemotherapy, so people are living longer, that's the same situation. Okay, same thing as a chronic disease is with new treatments. The prevalence is going up, compared to the incidence rate, just because people are living longer. Now, this is really tricky too, but it's important. It was in your notes. And so the increased prevalence of the disease is going to increase your positive predictive value. And that just means there are more people in the population that will test positive. So in sheer numbers, your positive predictive value will go up. All right, because it's just more common in the population. All right, and we did talk about this previously. Precision, we're looking at a clustering pattern, right? Whereas accuracy is around the bullseye, and this is what we want. We want accurate around the bullseye, plus we want it precise, okay? We want this clustering pattern, okay? This is what I was talking about. This is part of the document I have with these equations. So gotta know them. If you could work out in your head kind of where everything fits in, it'll help you out. But again, they're gonna give you those tables. So it's gonna make it, it really does make it a lot easier. So don't stress about it. All right. I don't wanna get into this too much. The only thing you really need to know is that the closer it is to your axis over here, the better the test is, right? So let me just do this. This is our area, so for the green line, this is our area under the curve. This is terrible. You get what I'm saying? So everything that falls under here is the area under the green curve. The greater area under the curve, the better the test is, the more accurate the test is. So I have it in first aid. This is kind of all you need to know. If they give you a question on this, they're just gonna ask you, they'll probably put A, B, C, and say which one's the best test. The closer you are to the X and Y over here, the more, the more of a right angle you're making up here, the better the test, because you have a higher area under the curve, greater area under the curve, okay? And that's what it says here. This is what defines it. They're not going to ask you to plot it out like in small group or anything like that. You just need to know, be able to read it. All right, these are a pain in the butt too. So we got this. The point of this is how likely the test is. So again, they're moving numerators and denominators, and then putting out in words. But the probability that a test would be positive in a person with the disease over the probability of positive test of a person without the disease. So that's in words saying what this equation is. What you really need to know is that if you have a higher number for a positive likelihood ratio, that's a good test, okay? That means your predictability of getting a positive test for a person with the disease versus a positive test for a person without the disease, which is not what you want, is good, okay? So you want a high number, you want a high numerator, okay? If the wording's confusing, just remember if they give you a graph, and the positive likelihood ratio is the highest number, okay? I think that's what they had on our test. They asked us what was the highest likelihood ratio, and you just pick the biggest number for positive. Now, negative likelihood ratio, you could read that here, negative for a person with the disease versus negative with a person without. So in this situation, a negative likelihood ratio, the lower number is a good test. So you're in the decimal point range. Did I put the graph? I did not put the graph, but there was like a table. Again, the highest number is a good positive likelihood ratio. The lowest number is a good negative likelihood ratio. That's the easiest down and dirty way to do it. All right, and you can see that here. And I like this because it kind of gives you a little definition. This is again from that little table in my additional resources with all the equations. Okay, so decreased odds after a negative result versus, yeah. So you can see that here. All right. This was a little confusing. I'm gonna explain it to you the way I understand it. So for parallel testing, we're looking at increased sensitivity. So they use this in situations where it's an urgent situation. You can give multiple tests at one time, okay? Now, the thing about this is if you had a good test for either sensitivity or specificity, you wouldn't have to do this. You wouldn't have to do parallel testing. You wouldn't have to do serial. You can give one test, say definitively, take the hemoglobin H1C, you definitely have diabetes. But these are situations where nothing's really great. There's a lot of gray area. So if somebody comes in urgently or whatnot, and you can run a bunch of tests simultaneously, if any of them test positive, that correlates to increased sensitivity. You're likely to have included the disease, okay? Now, serial testing, again, this is a situation where none of the individual tests correlate to a very good specificity. None of them can definitively rule out the disease. So you use multiple tests in sequence to figure it out. So the example I would use is saying, if you were using tumor markers, serum tumor markers, right? But they're all, they're broad, they're not specific. They're, so these tumor markers are non-specific, right? But so you run a couple of tumor markers, all non-specific. None of them definitively say you have the disease, but if all of them test negative, it tells you probably don't have the disease, right? Hope that made sense. So think about it as tumor markers that, like rheumatoid arthritis. There's a lot of inflammatory markers that show up that are very non-specific. They don't necessarily tell you you have rheumatoid arthritis, but they tell you you have inflammation. Okay, so if all of these inflammatory markers are negative, well, you're showing that you don't have inflammation, so you likely don't have rheumatoid arthritis. But if one of these in sequence says there is inflammation, then it is possible, okay? So again, if it's still confusing, just memorize parallel, increased sensitivity, serial, increased specificity. But the thought processes here is none of these individual tests are great. So you have to use multiple. All right, and this is in words. Yeah, increases sensitivity, you do them in parallel. And obviously, what I was just explaining, this sensitivity correlates to a high negative predictive value, okay? Increased sensitivity means increased negative predictive value. And then here, specificity, and that correlates to your positive predictive value. That's your spin snout thing. And again, yeah, like I said, none of these individual tests are really great. So you work with what you have. All right, you can read that here. Okay, so probability versus odds. We'll look at this. So probability, remember, it correlates to everything. So, and odds is you correlate to positives over negatives. So it's more of a ratio, where risk is like people with the disease over the entire population, and odds would be people with the disease versus people that don't have the disease. Okay. Just in case they ask, it would be good to know which of these tests are more valid. Remember, meta-analysis takes data from a bunch of different research papers and sites and puts everything together. So just knowing which ones, easy points, if they give you a list and say which is the most valid, you always want to go with meta-analysis. And then observational studies obviously aren't as good as experimental designs, because experimental designs, you could design it around what you're actually testing. Okay, so just knowing which ones are better, which ones show increased validity, will get you points on that. All right, so I'm explaining this the simplest way as possible. I think Dr. Hernandez, the way he kept harping on the idea of this, you want to determine whether we're looking, are we studying the exposure or are we studying the disease? Okay, so for cross-sectional, we're going through, we're just looking at one snapshot in time, right? You're actually looking at the exposure and the disease together concurrently. Okay, so you're just going to analyze everything at a single period in time. So it kind of explains here, collection relevant data at a specific point of time. So this is the easy one. Okay, exposure and disease together. Now, if we were looking at a case control study, you can see here, it's retrospective. So case control, you start with the disease, okay? And so we're saying, lung cancer. We're starting with lung cancer, and we're gonna look back. We're gonna say, what was the cause of the lung cancer? So it may come down to smoking or whatnot. The point is, in the stem of the question, they're gonna say, we're looking at the disease and we're trying to look back and see what caused the disease. So that's a case control study. That's all you really need to focus on. Are we talking about the disease? Are we talking about the exposure? Which one are we trying? Which one are we starting with and which one are we analyzing? So for case control, you're starting with the disease and you're looking at what could have caused it. And you can see that here. We're looking at this disease, people that have it, people that don't have it. We're going back in time and seeing if they were exposed, who was exposed and who wasn't, what could have caused it, okay? So like mesothelioma, great example, right? That's that, cancer from asbestos, in the plural of the lung. So people had mesothelioma, first couple of people that came up with it, like, what is this weird cancer in the pleura? And they had to go back in time. They said, what were these people exposed to previously, maybe 40 years ago, that could have caused it? And then they were able to whittle it down to say there was an asbestos exposure, okay? Now, when we do these case control studies, we can look at odds ratios. So I think the idea, they probably won't ask you to calculate this, but just to see if you could set it up properly. So they'll give you this and they'll say it's a case control study, or they'll say they want the odds ratio, and you just need to put it together. Remember, A over C over B over D. Once you flip it and reverse it, you get A over D over B over C. So that's going to be your odds ratio. So it should be fairly simple. As long as you could set it up, you're good. All right, explains it here. Now, ecological studies are just, in case I think we did have a question on this, pretty simple. We're talking about populations, not individual people, okay? So when you're looking at populations, that's your analysis, consider it ecological. All right, now, these cohort studies, we're looking at the exposure first. Now, whether we look at prospective or retrospectively, it's the exposure we're talking about, okay? People were exposed to cigarette smoke. They've been smoking. What is the consequence? So you can go forward in time. You could say, okay, these people are exposed, and you could follow them through time, or you could go back in time, right? They were exposed to cigarettes. They were exposed to cigarettes, and what was the consequence of that, right? So for these cohort studies, remember looking at exposure first. All right, so these people were exposed to cigarettes, right? What were the long-term consequences? So this is prospective study, what was the consequence in the future? You follow them and see what happens, right? Or like radiation, something like that would be a good one. Chernobyl, right? They were exposed to it, follow them over the next couple of years, see what develops. And then when we look at these cohort studies, that's when we talk about relative risk. So again, you need to know these, but I think as long as you could set these up, you should be good. They'll give you the table, they'll ask you relative risk, just plug it in and get it right. All right, again, relative risk, see that here. Then we could talk about some more definitions, attributable risk. So what is the incidence in the group versus the incidence in the non-exposed group? So we could take that data and look at what were the consequences. And then you could obviously put that into a fraction. So also you could do absolute risk reduction. So again, they're gonna have to make it very straightforward for you on the test. They're gonna ask you what exactly you're looking for. How do you calculate the absolute risk reduction? So we know that this is the case. Attributable risk is the EER, or this, minus the CER, this. Just remember, absolute means that you don't have a positive or negative. You don't have a value. Absolute means it's gonna be positive. So it's either EER minus CER, it doesn't matter which way you do it because the negative value goes away. It's always going to be positive. All right, it's absolute. Okay, so it should be fairly straightforward when they ask you about this. And as long as you know these equations, I think you'll be okay. All right. And then they do the number needed to harm versus the number needed to treat. And again, you just need to know the equation, number needed to harm. I thought I had the other one. Oh, there's number needed to treat as well, which is 1 over the attributable risk. But number needed to harm is absolute risk reduction, okay? So these numbers actually do come out to be similar. It just depends, or the same. It just depends if they're talking about treatment versus harm. Okay, we're almost done with this stuff. So don't get this, these are easy points as well. These randomized controlled trials, they go through different phases. So the initial phase, you're looking for safety. What are the side effects that could happen? Very small group of numbers. Then you can increase to phase 2, and you can get more people. You're looking at the efficacy. So you're starting to look at the dosing rate and stuff like that of the drugs. Then you go to phase 3, you get a lot more people. So you're looking at differences in side effect profiles, right, with more people. Then it goes to market, and phase 4 is post-market. So post-market, you're trying to see, you know, once you have millions of people or hundreds of thousands of people, did anything erratic happen? You know, the increased numbers should show increase, you know, any variability there. So just make sure you can determine if they give you one of these controlled trial phases, you could put it where it needs to be. Okay, we did have a question about this. This should be pretty straightforward. When you do this crossover study, you do treat both groups. So you start with one, the other becomes your control. There's always has to be a washout period where the drug or medication that you're using or whatnot has to get out of the system, and then you switch. All right. So this is this randomization type trial, but even though you randomize it, both groups get treated. Okay. Okay. Now, I could go through the biases, but I think first aid does a really good job of it. They are close together, and some of them are tricky. My advice would be to have a good example for each. I think some of these examples are better explanations than the actual definitions. So if you have an example that makes sense in your head for these different biases, it should be the same on the exam. You should be able to do that. So read through these in first aid. This is what they have. And if you can understand the different explanations or the examples, then you should be good to go. Okay, that's all for that. Hope that wasn't too bad. Does anybody have any questions? I did my best.